Let us solve problems which have appeared in mechanical engineering paper of GATE from the chapter on stress transformation. This is chapter number 6 in the booklet. The first question is the state of plane stress at a point is given by sigma x equal to. So we have a plane stress condition, which means there are two individual stresses. It is given sigma x is minus 200 MPa and sigma y is 100 MPa and tau xy is also 100 MPa. The maximum shear stress in MPa is, so it's a straightforward thing. So the maximum shear stress tau max is given by sigma x minus sigma y by 2 square plus tau xy square and square root of this thing. So if we just substitute the values, so it is minus 200 minus 100 divided by 2 square plus tau xy is 100 square. This is nothing but, this is minus 300 by 2 is 150 square plus 100 square. This is 225,000 plus 10,000. So that is square root of 325,000. Now if you find out the square root of 325,000, that will come close to around 180. Because square of 180 is 324, so this will come around, square root of 18 is 324, or square root of 180 is 32,400. So this square root will be something close to 180 MPa. So let's see the options and figure out what is the correct answer. The first option is 111.8, second option is 150.1, third option is 180.3, and fourth option is 223.6. So obviously C is the right answer. Let's see question number 2. Question number 2 is, if the principal stresses in a plane stress problem are sigma 1 equal to 100 MPa. So these are the principal stresses. Sigma 1 is 100 MPa and sigma 2 is 40 MPa. These are the two principal stresses. They have been given to us. Now let's see what is asked. What is asked is the magnitude of the maximum shear stress. It's very easy. Maximum shear stress is nothing but sigma 1 minus sigma 2 upon 2. So that gives us 100 minus 40 upon 2. That is 60 upon 2. That is 30. That's the answer. So let us see the options. A is 60, B is 50, C is 30, and D is 20. So obviously option C is the right option. This is 60, I'm sorry. Yeah. Now let's see question number 3. Question number 3 is, a solid circular shaft of diameter d is subjected to a combined bending moment and torque. Yeah. So there is a combined loading on a circular shaft. So there is a circular shaft like this, and it has, if I draw the axis, it has one torque T as well as one bending moment M acting on it. So this is the condition which is given. So, and the material property to be used, okay, what is the material property which has to be used? Such that the design of this shaft is done using the relationship 16 upon pi d cube square root of m square plus t square. Obviously this is the case when we use the maximum shear stress, because what we are telling here is that this portion is the principal stress and is the shear stress portion. So this relation, only in tau max we get square root of sigma x minus sigma y by 2 whole square plus tau square. This is analogous to this relationship, because this sigma x minus sigma y by 2 is analogous to m and tau is analogous to the torsion. So obviously we are designing using shear stress relationship or the torsional stress relationship. So let's see the options which have been provided. Option A is UTS or SU. That is not correct. Option B is tensile yield strength SY. That is also not correct. Option C is torsional yield strength or SSY, which is the right answer. And option D is endurance. So because there is no fatigue, so there is no question of endurance here. So this is also wrong. The correct answer is torsional yield or what is known as shear yield. Let's see question number 4. A solid circular shaft of diameter 100 millimeter is subjected to an axial stress of 50 MPa. Okay, so there is an axial stress. So there is a solid circular shaft and there is an axial stress sigma x, let's say, which is equal to 50 MPa. I will not write MPa, it is assumed to be MPa. Which means if nothing is written, it is assumed it is MPa. Now it is further subjected to a torque of 10 kilonewton meter. The maximum principal stress experienced on the shaft is closest to. So now this diameter is 100 millimeter and there is a torque of 10 kilonewton meter. So now let's see what is the maximum shear stress because of torque. Tau max is 16 times T upon pi d cube. So that gives me 16 into 10 to the power 3 Newton meter divided by pi into 0.1 cube. So this gives me, this is the maximum shear stress which occurs in this shaft, right? So this if you do the calculation for this, and this comes to around 51 MPa. It's easy to see how it will come to this pi is 3.14. We can divide this will become 5 something. So 16 upon 3 is around 5. So it's around 51 MPa. Now this is 51 MPa, which is the shear stress. Now the principal stress, so sigma P max is sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 square plus tau square. Correct? Now we have no sigma y, only sigma x is there. So sigma x is 50 upon 2 because sigma y is 0. And again this is 50 upon 2 square plus 51 square. So if this is 25 plus square root of 25 square plus 51 square. So now if we do this calculation, this is 25 square plus 51 square will come to some number. Now if we do the calculation, that's around this becomes around 25 plus 57, so that's around 82 MPa. So let's see the options. Option A is 41, option B is 82, option C is 164, and option D is 204. Obviously option B is the right option. Now let's see question number 5. A two-dimensional fluid element, okay, a fluid element is there. Now this element rotates like a rigid body. So in question 5, we have a fluid element. Now fluid element has a peculiar property that all directions have same stress, which is nothing but the pressure on the fluid element, PP kind of thing. Now it is rotating like a rigid body. At a point within the element, the pressure is 1 unit. So everywhere the pressure is 1. This is 1, this is 1, and this is 1. That's a condition which is given to us. The radius of Mohr circle characterizing the stress state at the point is now the radius of Mohr circle. So Mohr circle radius is r, which is nothing but square root of sigma x minus sigma y by 2 square plus tau xy square. That is nothing but the maximum shear stress in the material. That's a more circular radius. So this, in this case, there is no tau and sigma x equal to sigma y, so this becomes 0. So answer is 0. Let's see our options. Option is 0.5, B is 0, C is 1 and D is 2. Obviously option B is the right option. Let's see question number 6. Now, question number 6 and 7 are linked and they have the following figure to be used. A machine frame shown in the figure is subjected to a horizontal force of 600 Newton parallel to Z direction. Okay, so this is the machine frame. There is a frame like this. Yeah, this is Z, this is X. So you cross Z and X, so this Y will become like this. Now this machine frame is like a circular, it has a circular cross section, and this arm is bent in X direction further like this, and there is a force of 600 Newton applied here. Now this is Z direction and the dimension around Z direction is 0.5 meter and the height in Y direction is 0.3 meter. The diameter is 30 millimeter, that is given to us. Now the normal and shear stress in MPa at point P. Okay, point P is lying here. This is point P. So what is the normal stress at point P? It's easy to find out. Normal stress is nothing but M upon I into Y, which is nothing but moment. What is the moment in this at this location? The moment is 600 multiplied by the height. The 600 into 0.3 Newton meter divided by I of circular cross section is pi by 64 into d to power 4. D is 0.03 meter into Y is d by 2, so 0.03 by 2. So if you solve this equation, you will get sigma is nothing but 67.9 MPa. So this is a maximum bending stress or the maximum normal stress. The maximum shear stress is nothing but 16T upon pi d cube, which is 16 into torsion. The value of torsion is, now you see value of torsion at point P will be nothing but this into this one. So this is 600 into 0.5 upon pi into d cube, which is 0.03 cube. So if you do this calculation, you will get this is around 56.6 MPa. So the pair, the normal and shear stress maximum values will be nothing but 67.9 and 56.6. Now let's see the options. First option is 67.9 and 56.6. Second option is 56.6 and 67.9. Third option C is 67.9 and 0, and option D is 0 and 56.6. So obviously we know that this option A is the right option here. Now let's go to question 7. Question 7 is linked to the previous one. The maximum principal stress in MPa and the orientation of the corresponding principal plane in degrees are respectively. Okay, maximum principal stress. Now what is the maximum principal stress? Sigma P max is nothing but sigma x plus sigma y by 2. In this case, because in this case what is happening is that because the plane of the cross section is xz. It is not yz actually. So we have to alter the definition now. But let's see, the formula is sigma x plus sigma y2 plus square root of sigma x minus sigma y by 2 square plus tau xy square. This is the normal way of writing the expression for maximum principal stress. But for this, we have to remember that the coordinate system is like this, x and y, where this is tau xy, this is sigma x, and this is sigma y. Okay, so this is sigma x, this is sigma y, and this is tau xy. This is the nomenclature. But in this case, that's not what is happening. In this case, it is not x and y, it is basically y and z actually, where I mean the element is lying in y and z and y and x plane. So at the point P again it is x and y only, so we can use this expression, yeah, because at point P what is happening is that point P is, this is a circle, this is point P, and this is z direction. So obviously this is x direction and that is y direction, so we can use this expression here, right? So we'll use this expression. Sigma P max is nothing but, now there is no sigma x, so sigma y is 67.9 upon 2 plus square root of sigma x is 0 minus sigma y by 2 is 67.9 by 2 square. Actually this is minus, and plus tau xy square. So tau xy is 56.6 square. So if you solve this equation, you will get this is 100 MPa. Angle, now tan 2 theta is 2 times tau xy upon sigma x minus sigma y. That's the relationship. So it is 2 into 56.6 upon sigma x is 0 minus sigma y is 67.9. So this is nothing but 2 theta is tan inverse of 1.66 approximately. So this is, you, if you do this calculation, you will get it's around minus 60 or something. Yeah, it's around, you'll get it's around minus 60, but which is also equal to around 120 degrees or 121 degrees. So the theta will be 120 by 2 is around 60 degrees. So the let's see which option is correct. Now option A here is, option A which is given is minus 32 and minus 29.52. Option B is 160.48. Option C is minus 32 and 60.48. And option D, I'll just write it here. Option D is, this is option C, and option D is 100 and minus 29.52. These are the four options. The first of these is the principal stress value, and the second is the angle value. Obviously principal stress is 100, so A and C are obviously out because the principal stress is not 100 in these cases. Only B and D will remain, and in case of B we are having 60.48, so that is the right answer. Actually B and D are same options actually, because 60.48 and minus 29.52, both of them will come. But what happens is that because the angle is positive, so we have to choose a positive angle first. So that's why 60.48 is the right answer in this case. Let's go to question. Right. So question number 8 is the Morse circle of plane stress for a point in a body is shown. Okay, there is a Morse circle which is shown, and the Morse circle is like this. It is here. Oh, I'm just drawing it without any scale. So this is 10 and this is minus 10 and minus 100, sorry. So this is the tau axis and this is sigma axis. The design is to be done Now this is a Mohr circle for the stress state in a body at particular point. The design has to be done on the basis of maximum shear stress theory for yielding. Now maximum shear stress theory, what does it say? That maximum shear stress, when the stress in the when the shear stress in the material exceeds the allowable maximum shear stress value, yielding happens or yielding ensues. It starts, it commences. This is the condition for that. Now let's see. The tau max value is approximately equal to the yield strength by 2. This is normally the condition. For ductile materials especially, this is the condition which is used. And the value of tau is equal to sigma 1 minus sigma 3 by 2. Now over here there is only one sigma 1 given. There is no sigma 3. So here it is minus 100 by minus 0 upon 2. So that is minus 50. So we have to say sigma y by 2 is equal to minus 50 MPa. And what is done is that because it is a strength number, so we take absolute value of this. So this is equal to this. So sigma y is 100 MPa. So that's the answer. So when the yield strength of the material is 100 MPa in this case. So let's see the options which are given. Option number A is 45, option B is 50, option C is 90, and option D is 100. This is the answer. See, don't get confused by in this formula here. In this formula, don't put sigma 1 minus sigma 2 by 2. That is not the right answer. It is always sigma 1 minus sigma 3 by 2. And for that, the value is because sigma 3 is not there, it's a plane stress condition. So in this case, the shear stress will be equal to minus 50. And because the yield strength is half of the tensile strength in yielding approximately, hence the tensile strength number will be double of the yield strength. So it is 100. Now question number 9. Question number 9 is the figure shows, figure which is drawn here. Now this is the figure. This is sigma x and this is sigma y. Now sigma x is tensile stress and sigma y is compressive stress. You see, this is applied in the opposite directions. The magnitude of the normal stress values in x and y directions are 100 and 20. So this is equal to 100 and this is 20. So I will put this as minus 20 because it is coming in the negative directions. So the value, now what is that we are supposed to say? The radius of Mohr circle. Now obviously the radius is, we know what is the radius. The radius is square root of sigma x minus sigma y by 2 square plus tau xy square. Now there is no tau xy in this case. There is only sigma x minus and sigma y. Sigma x is 100 minus sigma y is minus 20 by 2 square. So this is nothing but 100 plus 20 upon 2, which is nothing but 60. So let's see the options which are there. Option A is 120, option B is 80, option C is 60, and option D is 40. So obviously option C is the right option. You have to just remember the formula for radius of the Mohr circle. Radius of Mohr circle is nothing but the maximum shear stress value. So that's it. Now question 10. A shaft subjected to torsion experiences a pure shear stress tau on the surface. Yeah, obviously it is subjected to torsion. It will be having only pure shear stress of tau on the surface. The maximum principal stress on the surface, which is at 45 degree to the axis, will have the value. Okay, now this is a shaft and it is subjected to torsion. T, some torsion, and it is causing shear stress of tau. So now let us see what happens is that, let's say we take this element here, some element like this, So that element is subjected to a tau, and because there is a complementary stress, so that is also tau. This will be tau and this is tau, like that. So it's all pure shear condition. Now when we orient the axis, or we orient the element to 45 degrees, 45 degree it will become like this, and in 45 degree direction it is only normal stress in this element, because the shear stress will get transferred to normal stress in 45 degree direction. And we know that the transformation rule is sigma is equal to sigma x cos square theta plus sigma y sin square theta plus 2 tau xy cos theta sin theta. This is the condition. Now in this plane there is no sigma x and there is no sigma y, so these are 0. Both of them are 0. So sigma is nothing but 2 into tau xy is tau into cos theta is 1 upon root 2 into sin theta is 1 upon root 2, because sin theta and cos theta are both 1 upon root 2 for 45 degrees. So this is nothing but tau. So let's see the option. Option number A is tau cos 45 degree. Option B is 2 tau cos 45 degree. Option C is tau cos square 45 degree. And option D is 2 tau sin 45 cos 45. Obviously this is the right option. We have solved it beyond that, but this is the right option. Option D. This is that same expression. This expression over here is same as option D. So this is question 10. Now let's see question 11. Question 11 is the state of stress at point P in a two-dimensional loading is such that Mohr's circle is a point located at 175 MPa on positive normal side. Okay. So Mohr's circle, this is question 11. Now we draw the Mohr's circle again. It's nothing big deal. This is the point 175 degree. 175 MPa, sorry. Now we know that when it is at the point, that is also the center of the circle. So center of circle is nothing but sigma x plus sigma y by 2. That's the center of circle. So that is equal to 175. And because there is no radius 0, that also means that square root of sigma x minus sigma y by 2 square plus tau xy square is 0, which means that individually both of these expressions are 0, which means tau xy is 0 and sigma x minus sigma y by 2 is also 0, which means nothing but sigma x is equal to sigma y. So both of these are equal, and if you put this condition here, we will get sigma x plus sigma x by 2 is same. So sigma x plus sigma y by 2 is nothing but sigma x plus sigma x by 2, because sigma x is equal to sigma y, which is nothing but 175. So we know that sigma x is equal to sigma y equal to 175. That's the condition. So let us see what options are given. Determine the maximum and minimum principal stresses respectively from the Mohr's circle. Now what is the maximum principal stress? Sigma p max is sigma x plus sigma y by 2 plus, and we can write the formula for minimum also, it becomes minus sigma x minus sigma y by 2 square plus tau square. This whole thing is 0 because the Mohr's circle is a point, and we know that these values are nothing but both of them 175, because sigma x equal to sigma y equal to 175. This is sigma x. So both of them are 175. So let's see the option. Option A is 175 and minus 175. Option B is 175 and 175. Option C is 0 and minus 175. And option D is 0, 0. So obviously now you first see the options. Option D is outright wrong. It cannot be 0 0, because if principal stress are 0, that means there is no stress, but there is a stress given 175, so it is not 0. So option D is outrightly wrong. Now because it's a point, so obviously both the principal stress are equal, so B is the right answer, which we have solved also now. Now let's see question 12. What does question 12 say? Determine the directions of maximum and minimum principal stresses at point P from Mohr circle. Now see, principal stresses are equal, which means every direction is principal stress direction. When the two principal stresses are equal, it is like a fluid pressure P. Every location, every direction on the fluid has the same pressure. Similarly, when principal stresses are equal, it directly means that from all directions the stresses are equal. So option, now in case 12 or question 12, the options are 0, 90. These are directions or the angles. Option B is 90, 0. Option C is 45, 135. And option D is all directions. So that is the right answer. It is all directions. Question 13. The number of components in a stress tensor defining stresses at a point in 3 dimensions is, obviously it is 6, because stress tensor in 3 dimensions is given by this: sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma, or actually this can be written as tau, 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 tau. Sorry, this is sigma, tau, this is tau, this is also tau, zy, and sigma zz. I'll write it once more. It is, the stress state is given by this matrix sigma xx, tau xy and tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, sigma zz. Now prima facie it seems that there are 9 elements, 9 independent numbers are required, but that's not correct, because the complementary elements tau xy is same as tau yx. We know that complementary stresses are equal, so this is equal to this, similarly this is equal to this, and this is equal to this. So there are only 6 independent numbers which are required. So option, now let's see the options. Option A is 3, option B is 4, option C is 6, and option D is 9. So option C is the right option. Now question number 14. Question 14 is the maximum principal stress for the stress state shown in the figure. The figure is like this. This is the figure for question 14. It is sigma, 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 and the shear stress is also equal to sigma. So now we know that what is the maximum principal stress for this. This maximum principal stress is sigma P max is sigma plus sigma by 2 plus square root of sigma minus sigma by 2 square plus sigma square. So this is sigma plus, this is square root of sigma square, which is sigma plus sigma 2 sigma. That is the answer. So the options which are given are, option A is sigma, option B is 2 sigma, option C is 3 sigma, and option D is 1.5 sigma. So option B is the right option. Let's see question number 15 now. Question 15. In a biaxial stress problem, the stresses in x and y directions are sigma x is equal to 200 and sigma y equal to 100. The maximum principal stress in MPa is, now biaxial stress state is given, and in this case we have sigma x and sigma y, which are given to be 200 and 100. This is a biaxial stress state direction, right? There is no stress, shear stress in this condition, that is sigma y and sigma x. Now see, there is no shear stress given, which means that these are principal stresses directly. So what is the maximum principal stress? It is directly given 200 because sigma x is 200. So that should be the maximum principal stress. So we know without even solving, the answer is 200. Let's see the options. Option A is 50. Option B is 100. Option C is 150. And option D is 200. So obviously the answer is D, 200 MPa. So these are all the questions which have appeared in last almost a decade in GATE Mechanical Engineering from the chapter on stress transformation. And I personally feel that this is the most important chapter in whole of strength of materials, because it deals with intricate theory, it goes deep down into the theoretical aspects, and it tells you how to transform the stresses, and it is highly mathematical also, and it gives you an insight into the theory of stress or the theory of elasticity, wherein we know how to transform the stresses from one plane to another and how to get the maximum stress values in a particular stress element or in a particular condition, which helps us in designing the element for strength. So in my opinion, this is a very important chapter. This is actually the most important chapter in my opinion. And everybody should do a lot of problems on this, especially on the transformation rules. Please try to remember the basic formulae directly without deriving them in the exam. There is no time to do that. Please remember the formulae for maximum principal stress and maximum shear stress, and the angles of maximum principal planes and maximum shear planes, as well as the transformation rule, which is like sigma in some direction will be equal to sigma x cos square theta plus sigma y sin square theta plus 2 tau sigma x sigma y 2 tau cos theta cos sin theta. Kind of these kind of formula should be remembered, and also remember that the angles are always positive counterclockwise, etc., etc., the sign convention. So in my opinion, if you know all these things, then these problems will be very, very easy to solve. And mostly every year there is at least one problem from this chapter. So it's a given that there will be one problem from this. So please solve as many problems from this chapter as possible.